Graphing with a rectangular coordinate system. So this section we are going to start looking at graphing on the XY graph. We're going to be plotting points, we're going to be drawing lines, we're going to do all sorts of stuff with graphing in this section. The objectives that we're going to cover is number 1, plot ordered pairs. Number 2, determine whether an ordered pair is a solution to an equation. Number 3, graphing linear equations. And number 4, graphing nonlinear equations. Objective 1, plot ordered pairs. So we need to define some of these terms that we're going to be using here. So when we're talking about graphing ordered pairs, an ordered pair is two numbers that are associated with a point on a graph. They are written in this formatting, parenthesis, x comma y, because it's helping us identify exactly where on this graph that single point would be. Now, those two numbers also help us be able to navigate to that spot. So the x value, that first number you'll see in an ordered pair, is going to tell us how far either to the left or to the right that we need to move. And then the y value is going to tell us from that spot how far either up or down we're going to need to move. Now, how we know which direction we move is based on positives and negatives. So if our x value is negative, we go to the left. And if it is positive, we go to the right. So positive goes that way, negative goes that way. For our y value, if it is positive, we move up. And if it is negative, we move down. And we will practice that in just a moment. Our second term here is a coordinate. So it's one of the numbers in that ordered pair. It could either be the x coordinate or it could be the y coordinate. But it's looking at one of the two numbers in the ordered pair. The x-axis is the horizontal line that is making up our rectangular system. And when you are looking at a graph, you'll notice it's a slightly darker line. I'll just point to it right here. It's this spot right here all the way across. That is your horizontal line, that is your x-axis. And oftentimes, if you look all the way over on the right, we often find a little X hovering by it, just as a little reminder. Sometimes it's there, sometimes it's not. Our y-axis is our vertical line. And I'll draw a line for that one. That is this one that goes up and down. Again, it's slightly bold. And if you look towards either end of it, you might see the little y. Again, sometimes those are there, sometimes they're not. And where these two axes cross each other is what's called the origin. So that is the spot in the dead center here. I'm going to put a red dot there. That is the ordered pair, 0, 0. Because we don't move anywhere left or right. We're not moving anywhere up or down. That is, in essence, our starting point. So when we are graphing points, we start there at the origin, and then we move either left, right, up, or down. Now, because these two axes cross each other, it creates like 4 regions to this graph. And those are what we call the quadrants, the 4 regions. Now, we typically name them with Roman numerals. So we're going to write the Roman numerals, but in essence, they are just named 1, 2, 3, and 4. It starts in this upper right-hand corner. That's the Roman numeral 1. It looks like a capital I. Then we go counterclockwise. So this area is the Roman numeral 2. Then underneath that is the Roman numeral 3. And then the last area is the 4. It looks like an I and then a V. So again, it's 1, 2, 3, and 4. They are commonly written as Roman numerals for those. So let's look at our first example. It says plot each ordered pair, and then we're going to state in which quadrant or on which axis the point will lie. So just as a quick reminder, I'm going to put it up at the top. For our x, y ordered pairs, our x value, if it's a positive x, it's going to move us to the right. If it's a negative x, it's going to move us to the left. And then after we've made that move, then we look at our y coordinate. If our y coordinate is positive, we're going to move up. And if our y coordinate is negative, we're going to move down. And then the number denotes how far we go. So let's try our first one. We have 3, 1. So from that origin spot, again, I'll put it in red there so we see it. We're going to move positive 3. So that's going to be to the right. 1, 2, 3. And then the y coordinate is a positive 1. So we're going to move up 1. And we're going to put it right here. And I'm going to erase off the little markings that I made to get us there, because the only thing that we need to leave on our graph is that final point that we made. So each ordered pair results in just a single dot on your graph. But sometimes it's helpful with a pencil to kind of hop on over there and hop up just so you don't lose track of your counting. And I'm going to put a little A next to this one so we don't forget that that was from part A. And if we think again about our quadrants, this would be in quadrant 1. So let's try our next one. We've got 2, negative 2. So our x value is positive, so we're going to go right, positive 2. And then our y coordinate is negative 2, which means we're going to go down 2. And we're going to make our point. I'm going to erase the other markings off of here. So the only thing left is our point for B. And if we count our quadrants, remember it's 1, 2, 3. That means point B is in quadrant 4. All right, let's try part C. We have negative 4, negative 3. Negative for an x value means we're going to move to the left this time. So we're going to go 1, 2, 3, 4 to the left. And then negative 3 is going to take us down for our y. 1, 2, 3. And we're going to mark that as our point C. If we count out our quadrants again, 1, 2, 3. C is in quadrant 3. Part D, we have 0, 1. For our x coordinate, we have the number 0, which means that it's not positive or negative. There's no number there, so we're not actually going to move. So we're going to stay where we are right here at the origin for our x coordinate. And for our y coordinate, it's a positive 1. So we're going to move up 1 to make our point. Erase off our extra markings. We'll label that one as D. And then notice it's not really in a quadrant. It's like on the line between quadrant 1 and quadrant 2. So whenever that happens and you end up with something on one of your axes lines, then we just label it based off which axes it's on. So we're going to say that it's not on a quadrant, it's on the y-axis. And then let's practice with our last one. We have 5, 0. 5 is our x spot. And since it's positive, that means we're going to move to the right 5. 1, 2, 3, 4, 5. And then we have a 0 in our y. So we are not going to move either up or down. We will stay right there. And again, that one is right on that line between quadrant 1 and 4. We don't want to pick either one of those quadrants because it's not in the quadrant. It's on the axes, and it is on our x-axis. Objective 2. Determine whether an ordered pair is a solution. Example 2. Determine whether 2 negative 6 is the solution of the equation 3x plus 2y equals negative 6. So what we are saying here is we want to take this ordered pair, which we know represents the points, x and y, and we want to plug it into this equation. And notice there's a spot for an x and a y. This term here, though, solution, is we're looking to see that if we plug the ordered pair in, we get that both sides are equal. We get something on the left equals something on the right, then we can say that this is a true solution. Now that terminology kind of sounds a little strange and new, but what that means is if I had graphed this and I graphed a line, that ordered pair that we are checking is actually on the line. That's what we're looking to find. If we plug in the x and the y and we get two different numbers at the end and they don't equal, which is why we put the slash through the equal sign, we will then say that it is a false solution. And what that means is if we graph the line, that the ordered pair is like off to the side. The line doesn't go through it at all. So those are like the two situations that could come out of this. So we're going to take 2 and plug it in for where the x is, and we're going to take negative 6 and plug it in where the y goes. So 3 times 2 plus 2 times negative 6 equals negative 6. Everything has been plugged in. Now we just want to simplify this problem out. 3 times 2 is 6. 2 times negative 6 is negative 12. We can subtract on the left-hand side to get negative 6. And then we check ourselves. Are both sides equal? Yes. So this is true. This is indeed a solution to this equation. And again, that means if we sketched it, it is a dot on our line. Let's try example 3. Determine whether negative 2 comma 3 is a solution to the equation 4x minus 3y equals 2. So again, ordered pairs are always given as x comma y. So we're going to plug negative 2 in where the x goes, and we're going to plug the 3 where the y goes. 4 times negative 2 minus 3 times 3 equals 2. 4 times negative 2 is negative 8. Negative 3 times 3 is negative 9. We can subtract to get negative 17. And negative 17 doesn't equal 2. So this is what we would call false. And again, had we graphed it, it would be like seeing the line and a dot just off to the side. They do not touch each other. Objective 3, graphing linear equations. Linear equations in two variables is what we're currently working with. These are equations that can be written in the form ax plus by equals c. So it kind of starts over here and finishes over there. Now, of note, the a, b, and c are real numbers. The x and the y here are standing for the variables. So that's what's going to help us get this on our xy coordinate graph. Example 4, graph the linear equation. Throughout this unit, we're going to talk about many different ways to graph. But for right now, the first method we're going to work with is what's called a t-chart, which means we're going to find values to plug in for either the x or the y variable to help us find the other variable, and that's going to give us a list of ordered pairs to graph with. Now this equation has a fraction in it. So I'm going to write it so you can see that fraction, 2 over 3 times x plus 1. Anytime you have a fraction next to a variable like x, we want to be very mindful of the numbers that we plug in. So I could pick any number I want for x to plug in. And most of the time, my go-to numbers are 0, 1, and 2. I like to keep things small. I like to keep them positive. It's just those are the go-to numbers that I have in my mind. But whenever I see there's a fraction involved, it makes life a little bit easier if you go by multiples of that denominator. So I can still use 0, but instead of plugging in a 1 or plugging in a 2, which would mean I'd have a fraction in my problem, I'm going to go with a 3, because 3 is a multiple of 3, or you could do 6, 9, 12. But I'm going to do 3 and negative 3. And the reason for my numbers is I glanced over here at this chart, this graph that I'm going to graph it on, and I notice what my limits are here. I've got to get something to put on this graph within these bounds. So negative 3, 0, and 3 are all within this graphing space. So those are the numbers I'm going to go with. So I'm going to take, and this is like scratch work, so I'm going to do it in green here for a second. I'm going to take my equation, y equals 2/3, and I'm going to plug in negative 3 where the x goes. And I'm going to get a result and put this in my chart, and I'm going to do this 3 times. So for each one of my x values, I'm going to plug it in and get an answer. So let's see. 2/3 times negative 3. Those 3's are canceling each other here. So I have negative 2 plus 1, which reduces to negative 1. I can fill in my chart. And then I'm going to do this again with my next x value. So 2/3 times 0. 0 times anything's all going to cancel. So I'm left with a 1. And then I've got 2/3 times 3. 3's are going to cancel, so I'm left with 2 plus 1. And I get y equals 3. Now each one of these is now an ordered pair that I can graph. Keep in mind your x moves you left and right. Your y moves you up and down. So our first ordered pair, negative 3, negative 1. Negative 3 takes us left. Negative 1 takes us down. Then we have 0, 1. So we don't go anywhere left or right from the origin, and we move up positive 1. And then my last one, 3, 3. I move to the right, positive 3, and then up for positive 3. I always recommend that you use 3 points to make a line. My MATLAB online tends to only use 2, so you would only need to put in 2, but 3 is the best way to make sure that all 3 are going in the same direction. You can create a line out of them. It's like checking your work for graphing. Let's try example 5. Graph the linear equation. We have negative 2x plus y equals negative 2. So we are going to make an xy table. We call this a t-chart. I don't see any fractions in this problem, so I'm not bound by trying to find a multiple of that denominator. So I'm going to use 0, 1, and 2. Those are my go-to numbers. So I'm going to write out my equation and plug in 0 where the x goes. 0 times negative 2 cancels. And I'm left with y is equal to negative 2. Then I'm going to write it again, and I'm going to plug in 1. Negative 2 times 1 is negative 2. I'm solving for y, so I can add this 2 to the other side. And I get y equals 4. I'm going to do this all one more time, but I'm going to plug in positive 2. Multiply to get negative 4. And then I'm going to add the 4 to both sides to get y equals positive 2. Oh, I made a mistake, didn't I, y'all? It looks like I missed a negative right here in my second attempt. So instead of that equaling 4, that should equal 0. Doop. We can fix that. And this is exactly why we always want to do 3 points. So we can look and see for when things don't quite work out. If all of a sudden you plot your 3 points and they look like a triangle, that gives you that reminder like, hey, let's go back. Let's make sure everything's working right in our math. But we should now have 3 ordered pairs. 0, negative 2, 1, comma 0, 2, comma 2. And once you get them on your paper, they'll look nice and straight. Connect the dots, go a little bit farther, and make sure you put those arrow points on the end. All right, objective 4, graphing nonlinear equations. So mixed into this section, you're going to have things that are straight lines and things that are not. Example 6, graph the parabola y equals x squared plus 2. So this problem gave you a little bit of hint in the title of the directions there, graph the parabola, that if you remember the term parabola, that means it's that U shape. It's either facing up or that U shape facing down. It's a quadratic function. So visually, you can see the equation and notice that this one has an exponent and all the other ones we've looked at so far don't. So exponent is our clue here that this one's going to be a little bit different, which means when we're doing our t-chart, while 3 points is the bare minimum, you might need to do a few more so that you can kind of see the full picture of what's happening with this graph. So let's see what we get when we get started with this. I'm going to start out with my 0, 1, and 2. I do like picking those 3 numbers. But then let's see what it looks like on the graph and if we need to add more. So I'm going to plug in 0 where the x goes. 0 squared is just 0. So I get a y value of 2. Then I'm going to plug in a 1 for the x. 1 times itself, which is what an exponent is. So 1 times itself is 1 plus the 2. We get y equals 3. We can plug in 2 where the x goes. 2 times itself gives us 4 plus 2. We get y equals 6. So let's take a moment then and graph these 3 and see what kind of shape we get from this. So 0, comma 2. 1, comma 3, 2, comma 6. We're just barely out, but you can notice if we kind of ballpark that number 6. Notice this is not a straight line. That's kind of like the thing to be careful with our nonlinears. So I'm going to go back to my t-chart and I'm going to add, let's do -1 and -2. Let's see what happens. So I'm going to keep going. I'm going to plug in -1 where my x goes. Now make sure you keep an eye on your parentheses here because -1 times itself gives us a +1. So this results in y equals 3. So if you put that point on, notice now it's even a more interesting shape, kind of like a check mark here. Then let's plug in -2. -2 times itself gives us a +4. So we result with y equals 6 up here. And so if we do our best to connect those points, we get a parabola. Let's try this one. Example 7, graph y equals the absolute value of x minus 3. So crash course real quick with those symbols. That's called the absolute value symbol. And what that does is it takes whatever value is in there and it measures its distance from 0. So whether it's a positive number or a negative, we just want the actual measured distance from 0. And what a lot of times people just kind of remember from absolute value is that everything that's inside absolute value always turns to a positive, because we are trying to find that distance between the values and 0, that it's always going to be a positive result. But that is what absolute value is the distance from 0. So let's make a t-chart. I'm going to go with 0, 1, and 2. The absolute value of 0 from 0 is 0. So when we plug in 0, we get a -3. When we plug in a +1, the distance between 0 and 1 is just 1. We can subtract the 3 and we get y is equal to -2. When we plug in a +2 into absolute value, the distance from 0 is 2. So we result with a y coordinate of -1. And if you glance at your graph of dotting those as we go, notice they are perfectly in line. So this is sometimes confused for being a linear equation, because if you just do those 3 and connect them and keep going, you miss what actually is happening on the other side. So let's add to this -1. If we plug in -1, where our x goes, the distance between -1 and 0 is 1. So 1 minus 3 gives us -2. And now it looks like a check mark. So if we keep on going and we keep finding x values to plug in, what you end up getting is this very sharp point, V. Absolute values always end up in a V shape. It's either a V shape facing up or a V shape facing down. But unlike the last one that was curved, that was a parabola, this one is absolute value. So they are very V-shaped. Let's try this one. Example 8. Graph y equals the square root of x. So let's make our t-chart. Find some values to plug in. Again, you can pick any x value you prefer. I tend to just stick with 0, 1, and 2. The square root of 0 is 0. The square root of 1 is 1. The square root of 2 is complicated. If you tried that one in your calculator, you're going to get a bunch of decimals. And we don't want to graph decimals. So we're not going to do 2. Let's try 3. See if you get decimals. I think we do. So let's try 4. You don't have to stick to the numbers of x that you originally pick. If you come across one that results in some crazy decimal or a fraction, you can pick different numbers. Remember, x values are things that you are picking for this problem. So if I plug in 4 underneath that square root, that gives me a nice pretty number. We get a whole number 2. So 4 comma 2. And square root ends up with this shape. It's like it starts like peaking up and then it kind of flattens out. It's almost like half of a parabola sideways here. But what you'll notice is that it doesn't go any farther to the left past 0. If you had tried to plug in any kind of negative number, you would very quickly get an error in your calculator because you cannot take the square root of a negative. So it does truly like start at one point and go out. That is your square root.